19th May GFG question, predecessor and successor. We are given a binary search tree and we have to find the predecessor and successor of the given target node. So predecessor is basically the largest node that is less than the key. The largest node that is less than, here in the first example, key is 8. So largest node that is less than 8, and successor is the smallest node that is greater than 8. So in this case, the successor is 9 and predecessor is 4. So this can be solved using a brute force approach of finding the in-order traversal of this BST. In-order traversal of a BST is always in the sorted order, that is its property, and we can just literally return the element that is on the left of this target element and on the right of this target element as our answer. 4 is predecessor, 9 is successor. So we can also omit the storing of the entire in-order traversal, since we are dealing with only these 3 things. We don't care about other things. So rather than storing all of that, we can have 2 conditions right here. So if the current value is less than key, for example, we are traversing in these things, right, 1, 4, 3 and all. If it is less than key, it can never be a successor, because in order for it to be a successor, it has to be greater than key. But since it is less, it can only be a predecessor. So we are checking if our old predecessor is null. For example, we encountered 1. There is nothing in predecessor yet. So 1 can be a candidate for predecessor. Actual predecessor is 4, but we will reach there. At least for now, the things that we have seen so far, we can conclude that, okay, one can be a predecessor. So that is why we assign 1 to our pre-variable. And suppose now we are at 4. So this not null is false, but this condition will get true. That is, the root data, that is 4. 4 is greater than our 1. So 4 is a better candidate for our predecessor. That is why we are again assigning 4 to our pre. And similarly, we do the same thing for this successor. This code will also get accepted if you submit it in GFG, right? But there is a slight better approach available. This takes off n complexity, time complexity. The space is constant in both this and optimal one. And the optimal one takes off h. So we are given a BST. So we basically always have to think of something in O of h, because that is the actual use of the properties of BST, right? So another property is that before finding the given key, the last seen greater value is successor and the last seen smaller value is predecessor. So basically what it is saying that, so here in the question, they have not asked the in-order predecessor and successors, right? They have asked the general predecessor and successors. So what is the difference? So wait a second. Whatever. Okay. So there, suppose the target was 9 instead of 8. So we have to return 10 as our successor. Why? Because 10 is the smallest element on the right subtree. That is our successor, the smallest element on right subtree. And what would be, in order predecessor? It would be the largest value on the left subtree. But that would be in order predecessor. Here we are asking just predecessor. So if they were asking in order predecessor, we would return null. But if they are asking predecessor, we have to return 8. So that is why this property is important, because 8 would be the last seen smaller value, right? Last seen smaller value than what? Then 9, right? So that we are storing that is a candidate of ours for our predecessor. Now suppose this 8 wasn't here, this was 7, okay? And here in the 9, we have 8 as our left child. So now the last seen smaller value would be 7. So 7 is a candidate for predecessor. If this 8 wasn't here, we have to return 7 as our predecessor. But in case there is something on the left subtree of this 9, that is the target value now, so we have to update our predecessor as the greatest value on this left subtree of 9. So that would be our 8. So 8 would be our final predecessor. So that is why the approach is working. So here I've written this in the algorithm like way. So if the current value of the node that we are at is less than key, what does it mean? That we haven't found the key yet. That is when we're dealing with, because if we found the key, we will just do the for successor, we would just find the smallest value, right, in this right subtree. And how do we find that? That is the leftmost element of the right subtree. And when we are dealing with the predecessor, that is the rightmost element of the left subtree. So those are our successor and predecessors. So if the current value is less than key, this can be a candidate for predecessor, right? Because suppose the key is not at all present. Suppose we are given the key as 11. So we have to, update our predecessor as 10 in this case, in this example, right? So that is why we are just always assign our predecessor and successors when these conditions occur as our candidates. So If the current is less than key, this is a candidate for predecessor, and we have to search right because key is greater than this element, and it is a BST. That is why we are omitting the left. That is how the complexity gets of H, because we're omitting the half search space and at each moment. So then if the current is greater than key, similar for successor, and we have to search for the left part for our key. Suppose in such a way the key got found, right? So just like I explained here, it's so messy, whatever, let's just see here. So yeah, so in this example, suppose there is nothing on the right side of 11 is the target basically, and there is nothing on the right side. So this 10 would be our candidate for predecessor. That is how we found it. But if there was something, suppose in the suppose this 10 was 9, just suppose, and in the left subtree of 11 there was 10. So that 10 would be our better predecessor, and that is why if the current is equals to key, suppose we found this 11, then the rightmost node of the left subtree would be our predecessor. Suppose this 10 was 8, and in the 11 we have, let's just copy this image first. Just delete this also. So just suppose that this is 8, all right, and here we have 9, and here we have 10. Of course it would be like this. So suppose if this tree was not at all here, then our predecessor was 8. So that is why here we assign it as candidate. But if this 11, that is our target node, if it has a left subtree, then the rightmost node, so of this left subtree, has to be the predecessor. So 9, and then we go as right as possible to find the largest value that is less than 11, right? We don't have to return any value that is less than 11. That is why we are finding the rightmost. And similarly, exactly same you can also do for successors. Okay, so this is basically what is written here. This is just a function to find the rightmost. So if there is a right element, we go as right as we can, as much right as possible, and this is as much left as possible. So there's a simple searching where at the current node, if the value of the current node is less than key, we assign a candidate for predecessor and we search for the right part. Otherwise we assign a candidate for successor and search for the left part. And then finally, if we found our key, then we find our most optimal predecessor and successor, all right, and then we return them.